Okay, like I said in the previous recording, in this remaining part of the lecture we're going to look at the two operations of insertion and deletion. So starting with insertion, as we all know, the idea of insertion is we want to insert a given key, call it V, into its correct place in a given binary search tree. And it's very similar to searching. Basically, we're going to be comparing our V against the root or x.key. If the V is greater, we're going to try and do the insertion on the right subtree. Otherwise, we do the insertion on the left subtree. We keep doing this checking, going left and right, until we find an empty tree. So when x is nil, then we have found the correct place to do the insertion. At that point, we're going to replace x with the new node containing the key V. Okay. Yeah, so here it says if V is less than y.key, where y is the parent of the x that was null, because we're going to make the new node to be a child of the parent of x. So the question is which child? Is it going to be the left child or the right child? So it depends on how V compares to the key of the parent y. If V is less than y.key, then we're going to put our V as a left child of y. Otherwise, the node containing V will be on the right child of y. So for example, suppose we want to insert 13 in this tree. I will show you the full detail of the example in the next slide, but here is the idea. We're going to use two references, x to reference the current node and y to be the parent, because when we find an x that is null, then we're going to create a child for the parent y to contain our new key. That's why we need the two references. So y is like a trailing point behind the x. Y is the parent of x. Let's take the example here. So this is the initial state. Initially, x is the root and y is nil. Okay, so we're going to compare x.key against 13. Obviously, 13 is greater, so we're going to go to the right. So when you go to the right, you're going to update your x to be x.right, and at that point y will be the previous value of x. So y will be the root. So this is what we have after one step. X has moved down to point to the node containing 18, and y is having the previous value of x, which is the root. So again, we repeat the comparison. Is 13 greater or less than 18? Obviously 13 is less than 18, so we're going to try to do this insertion on the left subtree. So at that point, you update y to become the current x, and then x to be x.left. So this is what you have in this step. So again, we repeat the question. Is x.key less than or equal to 13? Clearly it is greater, so we're going to try to go to the left. Okay, so update x to be x.left, which in this case is going to be nil, and update y to be the current value of x. And this is the point to do the insertion. Once we find x is nil, then we just need to create a new node to be to be a child of 15. The question is which child, depending on how 13 compares with 15. Since 13 is smaller, we're going to create a left child for this node 15 and put our 13 inside. So this is the final answer for the algorithm. So this is basically how insertion works. And here is the full algorithm. Okay, we start with T as the root of the tree, and Z is the node that we want to insert. Okay, so remember, in this course, the parameter here is not a key, actually it's a full node. So you have to create a node first before you call this algorithm. So Z dot key is actually what we want to insert, but we have already created a node and we pass it to this algorithm. Okay, so first we initialize y to nil as we saw in that example, and x to be t dot root. Then we start a loop as long as x is not nil, and all we shall be doing in the loop first of all, update y to be equal to the current value of x, and then update x to be either x dot left or x dot right, depending on how z dot key compares with x dot key. So if the key we are inserting is less than x dot key, then we're going to do the insertion on the left. So x becomes x dot left. On the other hand, if what we are inserting is greater, then x becomes x dot right. So this loop continues until we find x that is nil. At that time, we are ready to do the insertion. And here is how to do the insertion. First of all, the parent of our new node z, of course, is going to be y. So z dot p becomes y. Okay, for example here, this is our z, so the parent of z becomes the node 15. Okay. Next is we check if y is nil. Okay, if y is nil means the parent is nil. So in fact, the original tree we were trying to do the insertion was empty, if that is the case. So in that case, we simply set the t dot root to be equal to z. There is nothing else to do. But if it is not nil, then we check if z dot key is less than y dot key, so the key we are inserting is smaller, then we have to set the left of our parent, left of y, so y dot left becomes the z, y dot left becomes z. This is the z. Okay, on the other hand, if z dot key is greater, we will set the right of y to be equal to the z. Yeah, so this is the insertion algorithm. First, you have to find the location to insert using a loop, and then the rest is just to do the necessary assignment. The only thing to remember is, in addition to setting the left or the right of the parent, we also have to set the parent of the new node. The new node z will have a parent, which is going to be y. This is the first thing we did. Z dot p becomes y. What is the running time? Again, we are going across the tree, level by level, so depending on the height of the tree. So the running time is big O of h. And this is the analysis. Obviously, the initialization here is constant, so big O of 1. And this loop is going across the height of the tree, so it's O of h. Okay, lines 3 until 7 is a loop that is going down the tree level by level, so the running time is big O of h. And the final set of assignments are just assignment. They do not involve any loop. From 8 to 13 is just assignment and comparison, so is constant, and therefore the overall running time is big O of h, as we already mentioned. That is it about insertion. The final operation is deletion. Okay, so the idea of deletion is that we are given a node Z and we want to delete it from the tree. Now here there are 4 cases, some of them trivial, and at least 1 or 2 of them are not trivial. The first case is if Z has no children at all. Simply make the parent of Z to point to nil. Okay, like here, if we want to delete 13 has no children, it's a leaf node, so just make the parent of 13, which is 12, to point to nil. So 12 has no right subtree. This is all we have to do. The parent of Z should point to nil. So just cut this link and make it nil, and this will be garbage collected. Yeah, so this is what we have as the result. This is case 1, where the node being deleted has no children at all. Second case, the node being deleted has 1 child. So in that case, the thing to do is make the parent of that node point to the only 1 child. There's only 1 child for Z, so the parent of Z should point to its grandchild, the child of Z. Similarly, the parent of Z should become the parent of the Z's child. Yeah, it's better with an example. So let us see what we are talking about. So this is our tree. We have a node Z that has only 1 child, the right child in this case, and we want to delete it. So to delete it, what we are saying is, first make the parent of Z to point to the Z's child. This is the pointer from the parent of Z. Let it go directly to the child. So it will point to R, as you can see here. Q will point to R directly. Similarly, the parent of Z becomes the parents of Z's child. In other words, this is a Z child. Its parent should go up to be to replace the pointer that's coming from Z, so that the parent of Z become parent of R in this case. So actually this is if you like, two-way direction. So first make Z to point to Z's child. So we are doing like this. Make the parent of Z rather, so Q will go here. Okay, make the parent of Z point to Z child. Okay, so we have like this. Secondly, the parent of Z becomes the parent of Z's child. In other words, the arrow going off for the parent will now go from R to Q. This is basically the idea. What about if it has a left child instead? Very similar. Yeah, so just make the parent go to the child and let the child have this parent as its parent. No longer Z is the parent, it is this one. So this is what you will have. So this is the case where the deletion, the delete node has only 1 child. This is a real example. 16 has only one child, right child, so we're gonna make 15 to point to the right child and 20 to point to this as its parent. So this is what we end up with. Yeah. Okay, next case is that Z has two children, but this involves two sub-cases actually. So we have the first case: Z has two children, but its successor Y is its right child. Z has two children, but its successor is its immediate right child. In that case, what you do is you replace Z by the right child, updating Y's left child to become Z's left child. What does that mean? Let's take an example. So here we are trying to delete node Z, and of course Z has two children, left and right, so it doesn't fall into any of the two cases we have seen before. However, the successor of Z, remember how to find the successor, is the minimum from the right, where we keep going to the left, and the leftmost is the successor. But in this case, the successor happened to be this node, the immediate right child of Y, because the left subtree is empty, left subtree is nil. So this is very easy to do. All you have to do is promote this Y to replace the Z. Okay, so the left child of Y, which is presently null, will actually point to the left child of Z, and the parent of Z will point to Y directly. So this is the result you're gonna get. Okay. So this is an example. Suppose we want to delete 15, and the successor of 15 happened to be its own right child. So very easy, just replace 15 with 16, and that's what you're gonna have. Yeah. Okay, the last case is where the successor is not an immediate right child. Successor is not an immediate right child. So Z has two children, and its successor Y is not its direct child. In that case, you have to do two steps. First, you have to replace Z by Y, updating Y's left child to become Z's left child. Then you delete Y. So the deletion becomes, instead of deleting Z, it now becomes deleting the successor Y. This is similar to what we did in data structure, or deletion by copying. We copy the successor to replace the delete node, and then delete the successor. Yeah, so let's see diagrammatically what this means. We want to delete Z, and the successor of Z is not immediate right child because there is a left subtree, so we have to keep going to the left until you find a node that has no left. That is the successor. So Y is the successor of Z. Okay, so what do we do? First, we replace the Z with the Y. That's what it says here. Replace Z by Y, updating Y's left child, so this one, which is nil at the moment, to become Z left child, so it will point to L. Okay. After that, now delete the Y. delete the y using case 2, because now y has only one child, so deleting it is trivial. Right, so this is basically the steps. First, actually, we replace y, we replace z with y, okay, and then delete the y. So when we delete the y, x will be promoted up to here, okay. And now when you complete the replacement, of course y will point to L, so that because y is going to replace the z, so y will point to L as its left child. The right child doesn't change, it is still R. Just like the z was having R as its right child, if we do the replacement with y, we're going to get the same thing. So this is how to do the deletion in this case. And there is a similar scenario. Well, this is the same case, but I'm just showing you a real example. We want to delete 5. Okay, 5 has 2 children. Moreover, the successor of 5 is not its immediate right child. We have to go deep and find the successor. The successor here is 6. So we're gonna replace the 5 with a 6 and then delete the 6. Okay, so that what you have is 6 will be here replacing the 5, and 6 has been deleted from here, so the only one child is going to be promoted to replace the 6, and this is the final answer. In terms of coding, the book tried to introduce an auxiliary method before implementing the actual algorithm or method that is doing the deletion. So we have an algorithm called transplant, or a routine or a method called transplant. So it says here, to facilitate the deletion, we define the transplant subroutine. This routine will replace one subtree U with another subtree V. How does it do it? When transplant replaces the subtree rooted at U with that rooted at V, U's parent becomes V's parent, and the U's parents end up having V as its appropriate child. So actually here there are two cases. Let's take them one by one, because it could be that, so we have U, I hope I can draw it. We have U. Now U could be a left child of some parent. Okay, let's call it P. Okay, but it could also be a right child of P. So this is U. Okay, now we want to replace U with another node V. We want to replace U with V. So it says to do that, we're gonna replace, so when we transplant the subtree rooted at a node U with the one rooted at V, this is what happened. U's parent becomes V's parent. So this is the pointer going to the parent. So the pointer of V will go to the parent of U. Okay, and similarly, U's parent ended up having V as the appropriate child. So this is where the two cases differ. Is appropriate child means depends on whether you was a left child or a right child. So if you was a right child, then the parent of you will have, rather if you was a left child, the parent of you will have V as the left child. Okay. Similarly, if you was a right child, in addition to making V to have the parent of you as its parent, the parent will also have V as a right child. So it can be a right child or a left child, depending on what U is related, how U is related to its parent. Is it its original left child or right child? This is what the transplant procedure is doing, and that's what we're going to see next. This is a transplant. So we receive a tree, T, and two references, U and V. We want to replace U with V. Okay, so first of all, check that U is actually not a root, because if U dot P is nil, then U has no parent, and therefore we're going to update the root of the tree to be our replacement node. So T dot root becomes V. Okay, so with that taken care of, let us now try to do the replacement. There are two things to do. First, we check if U is equal to U dot P dot left. What does that mean? It means if U is a left child of its parent. To see that, let's do the drawing again. This is our parent, and this is U. Okay, so U dot P is here. So U dot P dot left, if it comes back to U, it means U is a left child of its parent. U dot P dot left. If that is equal to U, okay, this is a reference to U, so it means U is a left child of its parent. If that is the case, we're gonna make the left child, we're gonna make V to be that left child. So U dot P dot left becomes V, becomes the V. So V becomes the new left child of the parent of U. On the other hand, if it was not, then it must be that U was a right child. So the right child of the parent of U will become V. Okay, because U was here, having being a right child of its parent. So in that case, we're gonna make V to be that right child, not U any longer. So it's saying U dot P dot right becomes V. So based on this, we have done one of the assignment. We have set the link from the parent to V. Next thing is to set the parent of V to be the parent of U. So we are saying here is if V is not nil, V dot parent becomes U dot parent. So V will point to the parent of the former parent of U as its new parent. This is basically what the transplant procedure is doing. And with that, we can now have the deletion routine. So the deletion routine tries to take care of all the 4 cases we have seen. The 2 trivial cases and the 2 non-trivial cases. Let's take them one by one. Okay, so this is our tree T, and this is another one I delete, Z. So the first question is Z dot left equal to nil? Meaning the Z has no left child. if that is the case, so Z has no left child. Okay, so it has only a right child. In that case, all we have to do is replace Z with the only one child. Okay, so that's what we are saying here. Transplant Z with Z dot right. This is Z dot right. So replace Z with the right child. On the other hand, if Z dot right is nil, so which is this case, Z dot right is nil, so again there's only one child. In that case, replace Z with the left child of Z. So we're going to promote this left to replace the Z. Now notice that although these two cases are only taking care of or seems to be taking care of the case where there is only one child, it is in fact also taking care of a leaf node. Because let us say our Z is in fact a leaf node. So this is nil and right is also nil. This is our Z. Let's see what the algorithm will do. It say if Z dot left is nil. Yes, Z dot left is nil. In that case, replace Z with Z dot right. Okay, well, Z dot right is nil, so basically you are replacing Z with nil. So if it has a parent, that parent will be pointing to nil. So this will take care of the case where the node being deleted is actually a leaf node. We don't have to take it specially here because this code will also work for that case as well. Good, so that takes care of the two trivial cases. Now we are left with the two non-trivial cases. So else, it means here that neither Z dot left is nil, nor Z dot right is nil. Both of them are not nil. In other words, Z has two children. So the first thing we do here is find the minimum from the right. Find the successor. Okay. If that successor is not having Y as its I mean, it's not having Z as its parent, so the successor is not an immediate right child of Y, I mean Z. Okay, we found a successor Y. Let me probably show the two diagrams because there are two cases here. One is where the successor is an immediate right child. This is this case. Or the case where the successor is not an immediate right child. Now, in this case, we have to do both this much and this much if the successor is not an immediate right child. However, if the successor is an immediate right child, then this is going to be false. So we will not do this much. We will only do this much. Okay, so let's see. Let's start by looking at this case, which is easier. Suppose the successor is indeed a right child. Okay, so Y dot P is equal to Z. In that case, we don't do this one. We only come here. Okay, so here it says replace Z with Y. So this is like here, replace Z with Y. Okay, so Y will come and replace the Z. Now make Y dot left, which is currently nil, to point to Z dot left. Okay, so Y will have L as its left child, and make the parent of Y to be the left child of Y to be Y. So Y dot left dot parent becomes y, no longer z. Before, the parent of this node was z. Now we're going to change it to y. So y dot left dot p becomes y. Yeah, so update the parent basically of this left node. So this is the case where we have a trivial case. The successor is an immediate right child of the node being deleted. What if the successor is not an immediate right child? In other words, y dot p is not equal to z. Remember, y is successor, so the parent of the successor is not equal to z. In that case, the first thing to do is transplant y with y dot right. Replace y with y dot right. Okay, so in that case, this is our y. We're gonna replace it with its right child. Promote the x to come here. Okay, and do the necessary update. For example, y dot right becomes z dot right. Y dot right becomes z dot right. So we're gonna, after doing this copying, we're gonna make the right child of y to actually be r. As you can see here, y becomes r, and y dot right dot p becomes y. So the parent of that r is no longer z, it is now y. The parent of r initially was z, now the parent should be the y. So we have done that. Now the next thing is to transplant y to replace z. So transplant z with y. So this is exactly what we did earlier. After making y to replace the z, we have to adjust the left and the parent pointer of the L. Okay, so after y becomes here, we say y dot left becomes z dot left, so it will point to the L. And similarly, the parent of y dot left, the parent of the L, it was z before, now let it be equal to y. So this is the routine. It's a little bit complex, but I'm sure with this diagram you can see what is happening. There are two trivial cases and two non-trivial cases. The two non-trivial cases, one of them is a little bit easier. We only need to do one transplant. But the other case where the successor is deep down, is not immediately to the right, we have to do two transplants, because we have to update the successor, the child of that successor to replace it, and then move the successor to replace the z. And this brings us to the end of all the operations of binary search tree. These are, in summary, the running time of the different algorithms that we have seen. All the methods will have big O of h. All the method will have big O of except what we didn't list here, which are the traversal method. Those one will have big O of n, because we have to visit each node. But the search, predecessor, successor, minimum, maximum, insert, and delete, they will all have big O of h as their running time. So now it depends on the balanced nature of the tree. If the tree is balanced, then this is log n. If not, it is somewhere in between log n and n, so we just say n. Okay, as usual, we have yeah, that's what we are saying here. These operations are fast if the height of the tree is small, or rather if the tree is balanced. As usual, we have list of exercises, so I will just read them out here. I think there is nothing much to explain. The first one says, for the set this of keys, draw a binary search tree of heights 2, 3, 4, 5, 6. So you can draw different types of binary search tree using these numbers, and this is asking you to make sure they are of this height. And then give a recursive algorithms that perform pre-order and post-order tree work. I gave you the algorithm for in order. You are now being asked to do the pre-order and the post-order. This is trivial. And this one is saying, suppose that we have numbers from 1 to 1000 in a binary search tree, and we want to search for the key 363. Which of the following sequences could not be the sequences of nodes examined? Which of these couldn't have been examined? This is actually a very easy example. All we are trying to make sure is you know the nature of binary search tree. As we know, if we are searching, we're going to keep going left and right. If the target is less than the current key, we go to the left. If it is greater than the current key, we go to the right. So if you take this example A, for example, first we search 2, okay, and we couldn't find 368. Obviously 368 is bigger than 2, so we will have gone to the right. Now we went to the right and we found 255, 252 rather, okay, and of course 252 didn't match our target. So since our target is greater, we still go to the right, and when we go to the right we found 401. Okay, 401. 401 is not our target, and it is greater than our target, so we go to the left, and when we go to the left we find 398. Okay, so basically this is what you're gonna do. Try to trace this path, draw the tree, and see if it violates the nature of BST. So far it has not violated anything because all the elements here are greater than 2. All the elements here are greater than 254. Also 348 is less than 401. Now for one of these cases there will be a violation, and that is the case you are asked to find. You say which of the following sequences could not have been the sequence of nodes examined. Okay, so far this looks okay, but if we have seen a number somewhere here to the left, for example, that is bigger, rather that is smaller than this 254, then we know something is wrong. We couldn't have found this number to the right of 254 if it is smaller. This is basically what the question is about. I leave you to examine all the rest and see which of them is wrong. Okay, the next one says write a recursive version of tree minimum and tree maximum. What I gave you were iterative versions, so now you are asked to find the recursive versions. Write the procedure tree predecessor. I gave you tree successor. It should be very easy to do tree predecessor. And then this one is saying give a recursive version of tree insert. The tree insert procedure that we saw was iterative. You are being asked to write a recursive version. And finally, it says we can sort a given set of numbers, a given set of n numbers, by first building a binary search tree containing these numbers, using tree insert repeatedly to insert the numbers one by one. In other words, we can first of all construct a binary search tree using the numbers, And since we know that if we do an in-order traversal of binary search tree, we have the element sorted, we can sort this element in this way. So first insert all the elements to construct a BST and then print it in order. The question is, what is the worst case and best case running time of this sorting algorithm? I hope the question is clear. Okay, so this comes to bring us to the end of this lecture. I will see you in the next lecture, which will be very interesting because it's going to be on a new topic that we have not seen before. Thank you very much.